And welcome to Toddcast number 48. Continuing on with free radicals. So just to rehash, we talked about what a free radical was. When you break a sigma bond, you have two homolytically have two individual atoms. They carry a single electron. You can also break a pi bond and end up with a biradical. So a molecule that has two atoms within the molecule that are free radicals. I mentioned the fact that this is called initiation. It can react by pulling H off a compound and X off a compound, some element off a compound, to transfer its free radical from the initiator to the next molecule and can propagate. Went through selectivity associated with chlorination, bromination. So we've done most of the chemistry portion of it. Even had some industrial applications, how these work. What I want to do in this particular one is just talk about just a wider range of industrial applications. So we talked about the dentistry application, how the blue light is used to initiate it. You form a plastic. So we'll talk about plastic formation, and we'll make analogies to what happens in bio. Now, biology molecules, polymers, are not necessarily free radical polymers. So you can form polymers by tons of different reactions. It's just that industrially, it's a pretty common process to make plastics through a free radical process. Okay, let me go ahead and just talk about an initiator. A free radical initiator is a molecule that is semi-stable. You can store it, but as soon as you apply light or initiate some sort of energy input, it'll break into free radicals, and those free radicals can then initiate further free radical chemistry to go on within other molecules. So what we mean by that is any bond that can be broken pretty easily and generate radicals, we can say is a free radical initiator. Most common forms we usually look at involve peroxides. This OO bond can very easily break, and when it does, you'll end up with that sigma bond's gone, and you have a radical on this O, radical on this O, in addition to its normal lone pairs. This radical is resonance stabilized with carbonyl, and the rest of the molecule can also help, but you break that OO bond. So OO, pretty common. There's also AIBN, fairly common. This one is not as easy to see what happens, but this bond right here, this bond right here can break. And when they do, you end up with two resonance stabilized tertiary free radicals. And then the nitrogen becomes N2. The two radicals combine and form a pi bond. But these two can initiate. So the original compound, reasonably stable, shine light on it, you trigger it, it can now go on to initiate other reactions. And the third one I want to mention, NBS. In this case, this is our unstable bond between N and Br. It can readily break and form free radicals. And then those free radicals can go on to do whatever chemistry you need them to. So for instance, N can be resonance stabilized by moving a radical up like as such. Moving the radical to the O. Can also do the same thing at the lower carbonyl. So these can form reasonably stable radical intermediates, and as such can be used to trigger other reactions. They're reactive, but they're not so reactive that they don't last for a sustained period of time. Okay, we're going to talk about NBS as it pertains to certain specific synthetic OChem reactions I want to do. We're going to talk about benzoyl peroxide in just I guess you can call it an antioxidant processing, but basically it can start triggering other free radicals or scoop up other free radicals along the way. And then AIBN. So we'll talk about how these initiate processes, but let's go ahead and look at NBS first. So NBS is helpful for me synthetically because if I can generate this free radical, as mentioned, those go this way and you end up with this species. This N free radical can generate a stable Br free radical. So when it breaks, this N is resonance stabilized, but the Br then becomes reactive. And we go into our hydrogen extraction followed by a halogen extraction process that we mentioned before. So if this Br can come in and take this allylic hydrogen, we could have also chosen the allylic one over here, same by symmetry. So I just, for ease of simplicity, drew it on this side. It comes in, extracts an H to make HBr, end up with an allylic free radical that can resonate over. That can go in, that can go there, and that can go there. So you could end up with this resonance structure. Double bond there and the free radical there. But by symmetry, it's the same thing. Double bond here with a free radical over here, or double bond here. So I'm going to use them all interchangeably. Okay. That's the first propagation step. Then this R free radical, stabilized because it has resonance, so secondary with resonance stability, can now react with a Br2. Pick up a Br, so the same thing we did before. That's going to come in here, that'll go there. And a Br minus, which can then start all over again and react with this. It's a way to selectively add a bromine to an allylic position. And again, the bromine could have gone there with a double bond there, but it's the same compound. Note you end up with a new chiral center, but it has no stereoselectivity. You're going to get equal parts R and S. So it's good for positioning. You can generate an allylic alkyl bromide, which is going to be really useful for synthesis, because we put a functional group here, it can sometimes, through resonance, help facilitate a future reaction or stabilize an intermediate, whatever we need it to do. But this is a useful reaction, useful initiator, to put an allylic bromine or an allylic chloride on a compound. Pretty much, we're only going to use it for bromine. Doesn't really matter what the difference between bromine and chlorine as far as this reaction goes. Bromine is better, and it doesn't really matter as far as a leaving group for future reactions. So we're going to brominate, and hopefully that seems okay. So it's just a standard OChem reaction. Just want to add more to your arsenal of things to know. So a couple propagation steps, and as you know, when you add up 2 propagation steps, we will see that this ultimately goes to this. So this compound plus Br2 will go to the brominated version plus HBr. That's your overall reaction, your radicals cancel, and you have that process. Okay, that's a chemical process. So free radical chemistry, it does actually go beyond just straight halogenation of an alkane. It can be used, that's a perfect example of something that's used both synthetically. But really what it's most useful for is coming up with industrial molecules. So I'm going to talk about polymers, then also going to talk about refrigerants. So designer molecules, and there's different cases, but occasionally we want to selectively chlorinate or fluorinate a molecule to change its physical properties so we can take advantage of it. So I want to talk about something called a refrigerant. So the process of refrigeration, more of a physics concept, it's called the Carnot cycle. I'll just start with some box. A room, a refrigerator, a cold room, a house, whatever you want to call it, but you want to air condition it. You want to cool it inside, which means you want to remove heat from the inside and put it on the outside. Okay, the process we're going to use is pretty straightforward physics, where I have a piston. So here's my piston system, here's my piston rod. So a mechanical piston that I can apply work to push it down, and in doing so, I can take what's known as a refrigerant. So a refrigerant is going to be this yellow compound. It's a yellow gas for now. So refrigerant is going to be this yellow compound. And when I compress it, I'm going to compress it into a liquid. So when it goes from a gas to a liquid, it is exothermic, which means it becomes a very hot liquid. So coming out of the side of this compressor, when I compress it down, is a hot liquid. It doesn't seem like it has enough time to cool down here, but if I put a series of coils in here and I blow a fan across it, I can actually cool it down from being a hot compressed liquid to medium hot to maybe room temperature. So it's naturally going to cool down and turn into room temp. So RT stands for room temp. Once it goes to room temp, I have a pressure valve, and then in the walls of this container, I have piping or coils that are on the inside of the walls. I'm just going to do it to, let's say, right there, where as soon as I put it in, it goes from a high pressure liquid, so a hot, high pressure liquid, back to room temperature and room pressure. And when it does that, you now have the liquid going back into a gas as soon as it enters here. So maybe it doesn't evaporate really quickly, so we have a kind of a slurry of liquid and gas. But then, as it goes through, it turns into a true gas. Going from a gas to a liquid is an endothermic process, which means it starts sucking up heat from wherever it can. The only spot to get heat is from inside the chamber. So the heat starts being sucked into the chamber walls, where it can be used to convert the liquid into a gas. Evaporation, endothermic process, as you perhaps have known, when you sweat and that water evaporates away, it sucks heat out of you. So as this liquid turns into a gas, as it evaporates, heat sucked in. And so finally what I can do is I can send this gas back into the chamber. And as it goes in, it eventually will get compressed, which means I'm going to have heat escaping. I'm going to do that in red, sorry. I want to have heat escaping the chamber. So ultimately, I'm going to take heat from inside here, put it in the walls of this gas. The refrigerant is going to be piped back out into the compressor. The compressor is going to compress, releases heat here, releases heat here. So you release heat outside of the system, and you absorb heat within the system. So it takes a cold system and makes it colder, takes a hot world and makes it hotter by pushing the heat out by doing work. So you put work in to this machine to get heat out. Okay, that's the physics of it. That's the mechanics of it. This class, OChem, isn't going to go into the mechanics of it. It is kind of cool how it works. Simplified model at best. But what's interesting is what material we use. This becomes absolutely paramount in making decisions on what the material should be. So we need a refrigerant. We have to worry about the properties. So it's got to be compressible, because we have to compress it in here. And so as a general rule, when molecules are small, you have like tiny little spheres, they can be compressed more easily. When they're larger molecules, they have a tendency to aggregate. They have intermolecular forces. They don't compress as cleanly and neatly. So small molecule will help. Have to have the right boiling point. If I want to make a freezer, this maybe has to be negative 10 degrees in the walls in Celsius. If I want an air conditioning or refrigerator, maybe it needs to be 10 degrees, positive 10, positive 15. If I want a cold room, maybe it needs to be negative 40. So I have to pick the right material, the right refrigerant, the right yellow compound here for what I want to do with it. And so something to make note of is the molecular weight of a compound and the polarity of a compound both will impact the boiling point. I want it to be stable. I certainly don't want it to be highly reactive. And I don't want it to react with materials. I don't want it to leak out and react with the environment. So I want it to be relatively stable as I can get it. And then probably most important of all, I don't want it to be flammable. So notice, see all that fire going on, and yet it doesn't burn. So non-flammable. So if we choose a carbon-based compound, which, because this is an OChem class, probably where I'm going with this, to be non-flammable means carbon has to start in a +4 oxidation state. To be stable, it's got to have bonds that are not highly reactive. Have the right boiling point. I need to pick the right device or correlate the boiling point to the device I need, and then pick the right molecular weight. And in compressible, again, it needs to be small. So a small molecule, low molecular weight to have a low boiling point. I'll adjust the polarity accordingly. It cannot decompose, and it cannot catch fire, meaning it has to be a +4. So some things to worry about. The only way you can get a +4 oxidation state is for carbon to be bonded to more electronegative atoms, such as nitrogen, oxygen, and the halogens. There are other more electronegative atoms, but those won't be as stable as these. So we'll start with CO. CO2 is carbon in a +4 oxidation state. So any compound we have that has carbon in a +4 oxidation state with 4 bonds to O, or counting pi bonds, is eventually going to decompose or turn into CO2. It's just inevitable. So if we have carbon oxygen to make up our +4, it's going to be unstable. It's going to eventually decompose, and it'll run out of refrigerant. For nitrogen, kind of the same story. It can decompose. Nitrogen doesn't want to have, I mean, maybe not as reactive as a CO bond, not as good a leaving group, but it still can react. And nitrogen compounds smell really bad. So if it leaks, you'll get a fish smell or whatever terrible smell you get from that. I'm sure you smelled ammonia. I'm sure you smelled methylamine. If you smelled any amine compound, you do not want it around anything. Okay, I need to erase my picture. I apologize for this. We're stuck with halogens. And so for a long time, they had a material known as freon. Freon was a chlorofluorocarbon. And there's different types. There's fluorine, or freon 12, freon 22, freon 24, different types. So very much like gasoline, different fuels are slightly different bonds, slightly different composition. Same thing with these compounds. So it was small, only 5 atoms total, low molecular weight, around 70 for the 2 chlorines, like 71, let's say, around 38 for the fluorines, and 12 for carbon. So we're talking 120-ish for molecular weight. Not bad. And then this one, very slightly polar. So boiling point in the 0 plus or minus a little bit, depending on how many fluorines and chlorines I put on there. Didn't decompose. Actually, fluorine's not a very good leaving group. Chlorine, in this instance, not a very good leaving group. And plus 4 oxidation state, because everything's more electronegative than carbon, so it doesn't burn. It was great. Fit all the criteria we needed. We used it in the 50s, 60s, 70s, before then as well, but it was very prevalent. But then they discovered some problem here. Ends up, yes, it was compressible. Yes, it had the right boiling point. Yes, it was non-flammable. But stable became open to debate. What happened with these molecules as they escaped from these cooling systems, they would go up through the atmosphere, and they eventually would start interacting with the free radicals they formed would interact with the ozone layer. So because the ozone layer was filtering out most of the UV radiation that would break these bonds, no big deal, but as they went higher in the atmosphere, got exposed to high energy photons, they became highly reactive. So couldn't use those. So what we ended up doing is designing slightly different molecules. So instead of using chlorofluorocarbons, got rid of the chlorines. Chlorine is a more damaging halogen. Replaced it with HFCs, hydrogen fluorocarbons. So notice these two here, and these two here. The dipole moment will go this way, dipole moment this way. It'll cancel, so it ends up being about 0 divides. This one has a large dipole moment there, a very small one there. So this one ends up being polar overall. Their masses are the same. So altogether, 2 carbons, 4 fluorines, and 2 hydrogens. Their masses aren't quite what the chlorofluorocarbon was, but because of the higher polarity, in this case, the non-polarity, we had greater flexibility in their boiling points. So by simply moving where the fluorines went, we could distill these off and end up with the trifluoro on one side, monofluoro on the other, or 2 like difluoro. And so these boiling points would be enough different because of polarity that we were able to design it for the refrigerant we needed. That's kind of what we use today. There are a few other refrigerants within the system, but perfect example of industrial design is kind of applies to chlorofluorocarbons because we just talked about chlorination and fluorination. And so some of the ways that would make these original compounds. Bromoform, for instance, was something they used as a pesticide to kill certain bugs. Like, have you ever seen strawberries when they get tinted? They usually put that in there. Chloroform and variations on that were used in refrigerants. So they started fluorinating the chlorocarbons. And so they've had historically a lot of usage. So it ties into this, which is kind of also cool to see just the mechanics of where OChem ties into other sciences. Okay, that maybe wasn't the most OChem-rich example, but still it's interesting how these things work. So what we choose and how chlorofluorocarbons or fluorocarbons or chlorocarbons, how we make them, how they're applicable in science. Okay. Probably a more specific OChem example is we can design something called a polymer. So a polymer is built from a series of monomers. Polymer can be as few as maybe 5, 6, 7 of the monomers connected to one another to make a short chain, up to thousands. And so all depends on what property we're trying to get going. So let's consider something called polystyrene. Monomer is styrene. Styrene is a benzene ring with a vinyl group attached, or a double bond, if you will. So here's my styrene. Notice it has a double bond, benzene ring, double bond, benzene ring, double bond, benzene ring. They're actually going to line up this way conveniently for me in solution. They're always moving around and rotating, but I'm going to line this up just for ease of showing the picture here. So I put one of those initiators in there, benzoyl peroxide, AIBN, one of those, and I shine just the right frequency of light so that I break that bond, the initiator, but don't affect any of the bonds in the benzene ring or this alkene sticking off. Then the initiator is going to take charge and get the reaction to go. So if the initiator, that radical, can interact with the first of many pi bonds, it can now go on here and generate a free radical. That free radical can now react with another double bond, another double bond, and so forth. Let me get rid of what I've written and show this process. So the initiator gets it going, and then it keeps on going. You end up with this long polymer. And depending on the stoichiometry of how much initiator I mix, how much monomer I have in solution, I make long chains, medium chains, short chains. I can design polystyrene. So I can start making the plastics that I want a little softer, a little harder, more brittle, more compact, more dense, more clear. I can start picking the alkene with whatever side chain I want to change the properties of these materials. So polystyrene, you probably have dealt with this with squirt bottles. It's a soft plastic. You can, it's malleable. You can squeeze it and it'll change shape. It returns to whatever shape if you structure it the right way. So very, very good for, I don't know, just soft plastics. You also probably flown in a plane, or if not, you've at least seen a jet flying overhead going to the airport. The plastics they use, polystyrene, would not be very good for the windshield in the cockpit, certainly wouldn't be very good for the windows next to the passenger seats. So usually we use something like polycarbonate, a much stronger plastic, a harder plastic, and those are not necessarily made by free radical processes, but there are some. There's some plastics that are. So this can be an entire course, talk about how we design plastics, but the free radical one, this is the basic gist behind it. So PVC, so many uses for PVC. So structural material, piping for plumbing systems, amongst many other things it's used for. But vinyl chloride is a double bond with a chlorine attached directly to the sp2 carbon. So here's my chlorine, here's my sp2 carbon. The same thing that happened before the initiator gets going. The weakest bond is actually the pi bond. The sp2 carbon to chlorine is not necessarily a really strong bond. We know chlorine can be a good link group, but not off of sp2 it isn't. Normally it's off of sp3. So the weaker bond is this pi bond. So same things before the initiator gets going. And the same thing we saw up there happens again. Okay. Just food for thought. So for this material, these rings are all kind of, I guess, jammed in together. It can rotate. It can do some weird sort of things the way it packs with other polystyrene molecules. Polyvinyl chloride is much smaller, so it packs more tightly. So even though this this polymer single strand might be very rigid, it's how it packs in with another one. So kind of like saturated and unsaturated fatty acids in cell membranes. Saturated creates more flexible molecules like this, but they pack more tightly, become much more rigid or less fluid cell membrane. Same thing with polymer property. The property of the individual molecules and how they interact affects one strand, but it may not affect how all the polymers behave together. So I'll leave this, just one last thing. If you took a polymer class, you can actually start trying to design specific polymers, certain melting points, certain curing points, hardness, reflective properties, transmittive properties, just biodegradability, you name it. And so you do that by designing mixtures. So somebody might say, hey, let's try half styrene and half vinyl chloride and see what happens. And depending on how you make it, how slowly, how you cure it, you're probably not going to get styrene, vinyl chloride, styrene, vinyl chloride, styrene, vinyl chloride sequentially. But you may get it closer to one than the other, one than the other. So it would have very predictable predictable properties. So I'll leave this one as just kind of an interesting little application of chemistry. And then how this applies to the class is just free radical chemistry can be sought out at synthesis, as we saw, polymer formation, as we saw, designing certain industrial molecules, as we saw. So it's just more applications than anything else. And hopefully these are the kind of things that make this interesting. How this will show up on a test can definitely like talk about a free radical polymerization mechanism, can definitely talk about properties of this polymer. So we'll talk more as we start going through homework. But for now, this one is done. One more free radical podcast to go. And we'll move on to the next chapter after that. So hopefully this all went well. And I will see you at the next podcast.